Hello, today we are going to continue the study of the Kepler problem, and we are going to introduce parabolic coordinates to see what equations of motion are we going to get. First, recall that the transformation to parabolic coordinates for two coordinates x and y is given by x equals to 1/2 u squared minus b squared, and then y equals u times b. Remember that in the Kepler problem we have a motion in two dimensions represented by the x and the y. So now we are changing these coordinates to new coordinates u and b. So also remember that the Kepler problem is defined with a potential energy given by minus k divided by r, where r is the square root of x squared plus y squared. Okay, so the Lagrangian in Cartesian coordinates for the Kepler problem is m divided by 2 x dot squared plus y dot squared, and then minus this potential energy, but with this minus we are going to get a plus, k divided by the square root of x squared plus y squared. So we need to make the change to the new parabolic coordinates to get a new Lagrangian. So we need to calculate first x dot, which is going to be 1/2, and then 2u dot minus 2b dot using the chain rule, which is just going to be u dot minus b dot. Then y dot is going to be equal to u dot b plus b dot u. Okay, perfect. So if we take this into the Lagrangian, we are going to get m divided by 2 and then x dot squared, but that is going to be u squared u dot squared minus 2u dot b dot plus b squared b dot squared, and then plus y dot squared, but that is plus u dot squared b squared plus 2u dot b dot u plus b dot squared u squared, and then plus k divided by, let's say, just r. So it's easy to see that these two terms cancel each other, and we are going to get that the Lagrangian is m divided by 2. And here we have this element, this other, and this other. We can take them as a product of two factors given by u squared plus b squared times u dot squared plus b dot squared. You see that if you multiply these two, you will get these four elements that I have here, and then plus k divided by r. Perfect, so this will be the Lagrangian in parabolic coordinates. So we are going to be interested now in finding what is the Hamiltonian of the Kepler problem. Remember that the Hamiltonian is defined as qi dot pi minus the Lagrangian. Remember that these two indices say that we need to make a double sum. So this will be q1 dot p1 plus q2 dot p2 minus L, because we have only two generalized coordinates. But of course here q1 is equal to x and q2 is equal to y, so we are going to say that this is equal to x dot px plus y dot py minus L. But using the parabolic coordinates, we are going to identify also that q1, maybe let's call it prime, can be seen as u, and q2 prime is equal to b. So this will be equivalent to u dot pu plus b dot pb minus L. Okay, and using the definition of the conjugate momenta, we know that pu is equal to the derivative of the Lagrangian with respect to u dot. But what will that be? Well, we will get m divided by 2 u squared plus b squared, the derivative of this with respect to u dot, which is 2u dot. So this gives us u dot times u squared plus b squared, and here we have an m. Due to the symmetry of the problem, we will get that PB is equal to mb dot u squared plus b squared. Okay, so if we take this into the definition of the Hamiltonian that we have here, we are going to get that the Hamiltonian function is mu dot squared times u squared plus b squared plus mb dot squared u squared plus b squared minus the Lagrangian, which is m divided by 2 u squared plus b squared u dot squared plus b dot squared minus, here we will have k divided by r, but we need to see what is r in parabolic coordinates. So r is equal to the square root of x squared plus y squared, and if you make the calculation, well, remember that x is equal to 1/2 u squared minus b squared, so this goes squared, and then plus ub squared. So if we develop this, we are going to get 1/4 of u to the fourth minus 2u squared b squared plus b to the fourth plus u squared b squared. Okay, so we can see this as the square root of, it would be 1/4 u to the fourth plus 1/4 b to the fourth, and then plus 1/2 u squared b squared. That can be seen as the square root of 1/2 u squared plus 1/2 b squared raised to the second power. So this can be seen as just 1/2 u squared plus b squared. So yeah, we get that r is equal to 1/2 u squared plus b squared. So if we want to take this into the Hamiltonian function, we will get here that we have u squared plus b squared divided by 2, but we are going to put that 2 over here. So this will be the Hamiltonian of the Kepler problem in parabolic coordinates. This will be the first important result of the lesson. Okay, but we are going to express this Hamiltonian in terms of the conjugate momentas pu and pv. So recall that the important thing is to erase the variables that are being differentiated with respect to time, in this case u dot and b dot. So our Hamiltonian still depends on u dot and b dot, but from these equations we get that u dot is equal to pu divided by m times u squared plus b squared, and from this we get that b dot is equal to pb divided by m u squared plus b squared. So, well, we are going to substitute that in our Hamiltonian to get that h is equal to m u dot squared, but that is pu squared divided by m squared u squared plus b squared squared, and then this multiplies u squared plus b squared plus m b dot squared, but that is very similar, pb squared m squared u squared plus b squared squared, and this multiplies u squared plus b squared, and then minus m divided by 2 u squared plus b squared, and here we are going to substitute u dot squared by pu squared m squared here, u squared plus b squared squared plus a b dot squared, but that will be pb squared divided by m squared u squared plus b squared squared, like this, and then minus 2k divided by u squared plus b squared. Okay, so this is going to be pu squared m u squared plus b squared, and let me take this as a common factor, looking that it is here and here, so it will multiply pu squared plus pv squared, and then we can express the next term as minus 1 divided by 2m times pu squared plus pv squared divided by u squared plus b squared, then minus 2k divided by u squared plus b squared. So finally, the Hamiltonian can be seen as 1 divided by 2m pu squared plus pv squared u squared plus b squared, just by simplifying these two elements, and then minus 2k divided by u squared plus b squared. Perfect. Again, well, this is the Hamiltonian in terms of the conjugate momentas and the new generalized coordinates u and b. Okay, we need to notice that this Hamiltonian doesn't depend explicitly on time. So that means that this h is going to be a constant of motion. So we are going to name that constant as E, that will represent the total energy of the system. So we can establish the next equation. Okay, perfect. This function can be defined looking that h is a constant of motion, and we are going to express, well, we are going to solve this equation for 2k to be able to introduce another function that will correspond to a new Hamiltonian. So if we solve this for 2k, we are going to get that 2k is equal to pu squared plus pv squared divided by 2m minus e times u squared plus b squared. Okay? So the auxiliary function that is going to be very important in this lesson is h sub e, which is going to be defined as pu squared plus pv squared divided by 2m minus e times u squared plus b squared. So in the same way h is equal to e, we can say that this is equivalent to say that h sub e is equal to 2k. Okay, so what we are going to do now is to observe this expression. We are going to leave this element alone, so that will be equivalent to pu squared plus pv squared to m equals u squared plus b squared h plus 2k. This is in order to make the same thing with this expression over here, and to see what is the relation between he and the Hamiltonian. You will see. If we make the same thing with this expression over here, we will get that pu squared plus pv squared divided by 2m is equal to he plus e times u squared plus b squared. So if we equate the right-hand sides of these equations, we will get that u squared plus b squared times h plus 2k is equal to he plus e u squared plus b squared, given that if we manage this expression, we will get that h minus e is equal to he minus 2k divided by u squared plus b squared. So again, this is a relation between h and h e, to see later that this h sub e is going to correspond to a new Hamiltonian. And to be able to find the Hamilton equations corresponding to this he, well, first of all, what we are going to do is to say that we are going to take a partial derivative with respect to w, where w corresponds to any of the new coordinates, which can be u, b, pu, and pv. Okay? If I write the partial of h with respect to w, I'm generalizing that I'm taking the derivative with respect to any of these variables. So the partial of h with respect to w is equal to the partial with respect to w of all this thing that is, well, h in terms of he. So if we take the partial derivative with respect to w here, we will get that this is equal to the partial with respect to w of all this thing. So we will get here he minus 2k divided by u squared plus b squared, which is going to be, well, 1 divided by u squared plus b squared, the derivative of he with respect to w. Okay, so this is a formula to find the derivative of the new Hamiltonian in terms of the derivative of the old Hamiltonian. So we can express that the partial of he with respect to w is equal to u squared plus b squared, the partial of h with respect to w. Okay, perfect. This equation will be useful later on. And for now, we are going to introduce another relation with a new parameter that will be tau. In this case, tau will be known as the fictitious time or the local time in some context, okay, or the local time. But that is not important right now. The change of variable that we are going to do is that d tau is going to be equal to dt divided by u squared plus b squared. You are about to see why. So for example, what happens if we want to calculate the derivative of u with respect to tau? Well, this would be equal to u squared plus b squared, the derivative of u with respect to time, because from here we see that dt can be seen as u squared plus b squared d tau, and the equivalent thing will be that the derivative with respect to tau is equal to u squared plus b squared, the derivative with respect to time. Okay, perfect. So in this case, looking that this is u dot, we can use the Hamilton equations to get u squared plus b squared times the partial derivative of the Hamiltonian with respect to pu. But according to this equation that we found, u squared plus v squared times the partial of h with respect to some variable is equal to the partial of the new Hamiltonian with respect to that variable. So this thing over here is just the partial of he with respect to pu. Okay, so this leads us to the derivative of u with respect to tau equals the partial of he with respect to pu. So you can see very easy that, well, this is something like analog to the Hamilton equations. This is like u dot equals to the partial of h with respect to pu, but now with the new Hamiltonian and with the new variable tau. Perfect. So if we do the same process, but now let's say we are going to do it with maybe pu. Let's take the derivative with respect to tau. This will be equal to u squared plus b squared, the derivative of pu with respect to time, using the Hamilton equations here, looking that this is pu dot. This can be seen as u squared plus b squared, and then times minus the partial of h with respect to u. But again, using the other formula that we found, this one, we will get that this is minus the partial of he with respect to u. So we get that the derivative of pu with respect to tau is equal to minus the partial of he with respect to u. Okay, perfect. So now we have two of the Hamilton equations with the new Hamiltonian. If we make the same process with the PB and the B, we will get that the derivative of B with respect to tau is equal to, well, the partial of HE with respect to PB, and that the derivative of PB with respect to tau is equal to minus the partial of HE with respect to B. Perfect. So here we have the complete four Hamilton equations for this new Hamiltonian. Okay, perfect. Very important result by now. So we are going to recall the definition of HE, which is pu squared plus pv squared divided by 2m minus e times u squared plus b squared. Something that we can see is that we can separate this function as two functions, one of u and pu and the other one of b and pb. For example, we can say that this is pu squared divided by 2m minus eu squared, and then plus pv squared divided by 2m minus eb squared. As you can see easily, here we have a function, let's say h1 of u and pu, and then a function h2 of b and pb. Okay, so well, these two functions sum to get HE, the new Hamiltonian. So we are not going to prove the next, but it is a proposition that is very important when you take an introduction course to the Hamiltonian formalism. It is that proposition. It says that if you have a Hamiltonian, if h is equal to a function of, let's say, h1 of q1 all the way up to qn, for example, and then p1 all the way up to pn, plus another function that is from qm plus 1 to, let's say, qm, and then pm plus 1 all the way up to pm. Yeah, if you have a Hamiltonian that has this structure, then we can say that h1 is a constant of motion. It is not very hard to prove. You can do it with the Poisson brackets. Maybe in a future lesson I will do it, but for now we are not going to prove it. Just we are going to take it as a fact. And as you can see, the Hamiltonian that we have here is actually of this form, because we only have here the u and the pu that will be equivalent to have the q1 and the p1, but we do not have any q2, q3, no. So that means that this h1 has this structure, and this h2 also has this structure. Perfect. So that means that if we remember, we said that if h is equal to the energy, he is equal to 2k. So that means that this he equals to 2k is a constant of motion, making that if h1 is a constant of motion due to this proposition, and he is also a constant of motion, that means that h2 needs to be also a constant of motion. And actually we can say that h1 plus h2 is equal to 2k. Perfect. Something easy to say will be that h1 is equal to k, and h2 is equal to k, but that will be a mistake. We do not know if this k is divided on 2 halves. If this 2k is divided in 2 halves, one for each h1 and h2, so we can expect that there is some difference between h1 and h2. So we could say something like this. We are going to say that h1 is equal to the variable k, and then plus a difference. We are going to name that difference as d, and h2 will be that k minus that difference. Okay? You can see easily that if we sum this, we will get 2k. Perfect. So, okay. Now that we have defined this, and we know what is the form of h1, we can say that pu squared divided by 2m minus eu squared is equal to k minus d, and pb squared divided by 2m minus eb squared is equal to k plus d. Okay, perfect. And of course, this d is also a constant of motion for obvious reasons. As you can see, in these two equations, we have the elements pu and pb. But we are able to find those values if we recall these 4 equations that we found recently. So with that, remember that we found that the derivative of u with respect to tau is equal to the partial of he with respect to pu, okay? But this will be the partial with respect to pu of he, which is a pu squared plus pv squared divided by 2m minus e times u squared plus b squared. And, well, if we take the derivative with respect to pu, we will get just pu divided by m, making that pu is equal to m times the derivative of u with respect to tau. If with something similar, we will find that PV is equal to m, the derivative of V with respect to tau. So if we take these results into these equations, this one and this one, we can say that PU is equal to this to get that m squared, the derivative of u with respect to tau squared divided by 2m minus eu squared is equal to k minus d, and that pv squared, that will be m squared, the derivative of u with respect to tau squared divided by 2m minus ev squared equals k plus d. Okay, so with this, for example, let's take the first equation. We are going to get that m divided by 2, the derivative of u with respect to tau squared, is equal to, let's say, k minus d plus eu squared. So this should not be a very hard differential equation to solve. Maybe if we take this derivative of u with respect to tau squared, we equal this to 2 divided by m times k minus d plus eu squared. Then we take the square root plus minus like this. We can see that du divided by the square root of 2 divided by m times k minus d plus eu squared is equal to plus or minus the integral, d tau. Yeah. With this, it is very easy to find a function of u in terms of tau, and remember that we have a relation between tau and the time. So this will be like the way to solve the equation that gives us the motion in the variable u. So we should take the integral here. If we take the integral here, we will get just the tau. So again, this gives us tau in terms of u, or u in terms of tau. Okay, so other interesting thing that we can do, and before that let me remark this result because it is important. Other interesting thing that we can do is to get back to these two equations, and you see that if we multiply, for example, this one by this v squared and this one by u squared, and then we subtract these equations, we can cancel this element that has an e. Okay, so what happens if we do that? Well, if we multiply the first equation by b squared, we will get b squared pu squared divided by 2m minus b squared eu squared equals b squared k minus d. And the other one, we multiply it by u squared to get u squared pv squared divided by 2m minus e u squared b squared equals u squared k plus d. So again, like I mentioned, we are going to subtract these equations, and we are going to get 1 divided by 2m b squared pu squared minus u squared pv squared. This will cancel, and here we are going to get k times b squared minus u squared, and then minus d u squared plus b squared. Okay, perfect. This is already giving us an expression for d in terms of the parabolic coordinates and the conjugate momentas. So already this expression is very important. But to be able to express this in a more intuitive way, we are going to switch now from parabolic coordinates to the Cartesian coordinates. So, and I need you to pay more attention in this part. Remember, well, we have now to generalize a switch, a change of coordinates given by this. Qi prime is equal to Qi as a function of Qj, like this. Okay, we are This equation here represents a change of coordinates, where the new coordinate prime is in terms of the old coordinates. Okay? So these prime coordinates will correspond to the u and v that we are using. Okay? So if we want to find the pi prime, which is the pu, for example, or the pv, using, well, we can use the definition of the Lagrangian formalism that tells us that the conjugate momenta is equal to the derivative of the Lagrangian with respect to the corresponding q of the pi. So this will be like this. Okay? So, but remember that this is a function of the old generalized coordinates, like this equation is telling us. So this can be seen using the chain rule as, and I missed a dot here, this is, again, using the chain rule, the derivative of L with respect to q, let's say j dot, times the derivative of this qj dot with respect to qi dot prime. Okay, again, we are using the chain rule. We take the derivative with respect to the old variable, and then we take the derivative of that variable with respect to the new variable. Okay, perfect. But we are interested in this part that we have here. What is this going to be? Well, we have that the derivative of qj dot with respect to qi prime dot. Again, we are going to use the chain rule, and we are going to use this expression. Okay, the first thing we need to do is to calculate what is qj dot. So let me put an arrow. This will be from this that qi prime dot is equal to, well, the derivative of qi prime with respect to some variable j, and then we are going to take the derivative of this variable with respect to time. So that will be qj dot. Okay, so now that we have this, using the chain rule, we can calculate this. So first we can say that this is equivalent to qi dot equals the derivative of qi with respect to qj prime times qj prime dot. Okay, I'm just switching the prime position to get this expression. Okay, now we have this. Then we can calculate this using the derivative of qi dot with respect to qj dot. Okay, but what will be that derivative? Well, if we take the derivative with respect to qj dot of this, we will only get this element that we have here. So we get the derivative of qi with respect to qj prime. And I forgot a prime here. Remember that we are calculating this. Okay, so this is telling us that we just need to take out this dot, and it is exactly the same. The derivative of qi dot with respect to a dot variable is equal to the derivative of that variable without the dot with respect to the variable without the dot. So we are going to use that formula to calculate, well, the transformations between the px and the pu, the py and the pv, and so on. So, for example, if we use this equation, this one, and recall that this element corresponds to the pj. So this is equal to pj, and then times this, which is the derivative of qj with respect to qi prime. Okay, so let me rewrite that equation here. Pi prime is equal to pj equals, the derivative of qj with respect to qi prime. Perfect. So what will be p1 prime? Well, that is, of course, pu. So we will get, looking that we have a double sum in the j index, this will be p1 the derivative of q1 with respect to q1 prime. But q1 prime is u. And p1 is, of course, px. And the derivative of q1 is the derivative of x with respect to u. Okay? But remember that we have a double sum. So we still need to add the second element, that is p2 times the derivative of q2 with respect to u. Again, this is not changing, okay? This index I is the same. Perfect. So p2 is, of course, py. q2 is the derivative of y with respect to u. Okay, perfect. So we get that pu is equal to px, the derivative of x with respect to u, plus py, the derivative of y with respect to u. Perfect. So now we have pu. Let's find pv. That is going to be, well, following this formula, p1, the derivative of q1 with respect to b, plus p2, the derivative of q2 with respect to b. That is going to be, of course, px, the derivative of x with respect to b, plus p2, which is py, the derivative of y with respect to b. And remember that we have a transformation for x, which is 1/2 u squared minus b squared, y equals u times b. So the derivative of x with respect to u is just u. The derivative of x with respect to b is equal to minus b. The derivative of y with respect to u is equal to b, and the derivative of y with respect to b is equal to u. So this means that pu is equal to px u plus py b. And pv is equal to px minus b, like this, and then plus pyu. Okay, perfect. So this relates the conjugate momentas in the parabolic coordinates with the coordinates in the Cartesian, the conjugate momentas in the Cartesian coordinates. Okay, so if we get back to our expression for d, let me rewrite this equation and solve it for d. I'm going to write it in this piece of the page. Okay, and we are going to use this expression to find a new expression for d. The first thing I want you to notice is that what happens if we calculate the square root of x squared plus y squared? I think we did it at the beginning of the lesson when we calculated the magnitude r. Okay, yeah, it is here. We have here that r is equal to the square root of x squared plus y squared, and we got that, well, it is equal to 1/2 u squared plus b squared. So this means that u squared plus b squared is equal to 2 times r. Okay, perfect. Where r, again, is the square root of x squared plus y squared. So, as you can see, here we have u squared plus b squared. So, we are going to rewrite that in terms of the r. Perfect. Another thing is that, well, we are going to substitute this PV and this PU. So, again, remember that x is equal to 1/2 u squared minus b squared. So, as you can see, this element that we have here can be seen as minus 2x from this equation. Okay, so we are going to get u squared times pv squared, but that is going to be px squared b squared minus 2pxb pyu plus py squared u squared minus, it would be, let me make some space, b squared pu squared, but that is px squared u squared plus 2px u pyb, and then plus py squared and b squared like this, all divided by 2m u squared plus b squared, and then plus k, and remember that we said this is minus 2x, and then this divides u squared plus b squared, but we said that was equal to 2r. Perfect. Okay, so what is this going to be? Well, first of all, something is going to get cancelled, of course. Here we have u squared, px squared, b squared, minus px squared, u squared, b squared. So this element goes with this. Okay, for now I think that is the only thing that gets cancelled. Okay, so if we work with this, we will get, here look that we can take a common factor of minus 2pxb pyu, and that will multiply u squared plus b squared. So this is minus 2px py bu times u squared plus b squared for this and for this. Then we will get plus py squared that multiplies u to the fourth plus, actually minus, right? Minus b to the fourth. Yeah, we take this as a common factor, the py squared. And then minus kx divided by r, and all this is divided by 2m u squared plus b squared. Okay, so we can cancel a 2 here. We can cancel this with this to get minus px py bu, which is of course y. Remember, y was equal to b times u. So we will get a y here. This is divided in an m. And then plus py squared divided by 2m u squared plus b squared, and this is a difference of squares, so we can factor as u squared plus b squared times u squared minus b squared. This cancels with this, we get minus kx divided by r, and this is equal to minus px pyy divided by m plus py squared divided by 2m u squared plus b squared. Sorry, this was cancelled already. And here we have again u squared minus b squared. Remember that we have that x is equal to this equation, and well, u squared minus b squared is equal to 2x. So this is equal to 2x. Perfect, so we will get 2x here. This cancels, and here we have minus kx divided by r. So again, d, which is the thing that we were calculating, don't forget, it is going to be equal to, okay, let me factor a py, and this would be minus pxy. Let me factor again 1 over m plus pyx, okay, minus kx divided by r. As you can identify, this is the z component of the angular momentum. Okay, recall, this is the x component of the linear momentum times the y component of the position vector. So remember that the angular momentum is the cross product between the linear momentum and the position vector. So this corresponds to the z component of the angular momentum, the, let's say, the Lz or maybe the L3 component. So this means that d is equal to py L3 divided by m minus kx divided by r. And it's very interesting to notice here that this is actually a factor of 1 divided by m that multiplies the x component of the vector that is known as a Laplace-Rung-Lenz vector. We know we have a video on the channel that explains something about that vector. We work with it, we defined it, and that vector actually is defined as A, that is equal to P cross the angular momentum, where P is of course the linear momentum, and then minus M K R. Yeah. And as you can see, we are first taking the x component, that is PYLZ minus MKX. This is the x component of this vector. But we are multiplying by a factor of 1 divided by m. So ax divided by m is equal to this divided by m, and we cancel this. So this is actually exactly what we have here. So that means, again, that the d that we found, which is a constant of motion, is equivalent to the x component of the Laplace-Rung-Lenz vector divided by m. So in other words, this is telling us that this component of the Laplace-Rung-Lenz vector is a constant of motion. And you may expect that it will happen not only with the x component, but with the y component will happen also. Okay, perfect. So it's been a long lesson for today. I think this is a good moment to finish the lesson.